Yeah. I was not, and I have a big sign here that says record. All right, so you have these three phases: liquid, blood, lymph fluid, in some cases, some of the digestive juices that are being secreted into your stomach and along your GI tract. All right, gas, oxygen. Those are one of your respiratory gases. Carbon dioxide, that's another respiratory gas. We even have nitrogen gas. Every time you pop your knuckles, did you know that you're not grinding bones, that you're releasing nitrogen gas? All right, it's usually in the gaseous form in your synovial fluid, but when you go through the popping of the knuckles, it undergoes a physical, here's some chemistry for you, a physical and physics, a physical state change, and it goes from its gaseous form, it gets dissolved into the actual synovial fluid. That's why when you try to go to pop your knuckle again, like right afterwards, it won't pop, because all that gas is in a different state in one of these forms of matter here, all right? Okay? All right, so we're going to start off, remember when we talked about last class, we talked about the levels of organization, starting off on the cellular level, the molecular level, then the cellular level, then the tissue level, and I'll go over that in a little bit as a reminder. All right, we're going to start with the simplest or the smallest, so we're going to start off with the atom, okay? So this is the truth. The atom is the smallest particle, okay, that we're going to be studying. And usually atoms are associated with elements, okay? And an element would be like gold, oxygen. Have you ever heard of the periodic table of elements? I don't have a picture in here, all right? But those are all the known elements in our universe that we know of as of right now, okay? So an atom is that smallest particle that's going to exhibit the chemical properties, and the chemical properties have to do with any of the properties that we're able to observe for that element. All right, that atom exhibits all the chemical properties of whatever the element that it's a part of. Okay, so we'll talk, and it's funny because on this slideshow I don't have the periodic table, which I kind of regret. I should have put it in, but I didn't. But don't worry about it. I'm not expecting you to know, all right, which elements are where on the periodic table. That's chemistry. This is biology. We're only going to go over a few of the simple ones, okay? So let's start off with here, okay? Like I said before, it is the simplest level of organization, okay? So we have our atoms, okay, smallest particles. All right, some terms that you also want to know. An ion, okay? If you want the short definition of what an ion is, all right, it is a charged particle, okay? Or you can use this definition here, okay? It's an atom or a group of atoms that either have a positive charge or a negative charge, okay? But the short and sweet of it is an atom is just a charged particle, and it's either going to be positively charged or negatively charged, okay? So now, when we take a couple atoms and we stick them together, now we form a molecule, okay? And they're stuck together, they attach to one another, all right, through attracting forces, all right, or through a chemical bond. And we'll talk about those, attracting forces in the chemical bond, okay? So think of atoms as just individual small molecules on their own, wandering around, doing whatever they're doing, okay? And then when we start to attach them to one another, all right, when they start to link up, then we get a molecule. All right, and if we have an atom that's charged, if it has a positive or negative charge, then it's an ion. Okay, we're going to deal a lot with ions. All right, throughout this course and next and in 211. Okay, so I'm telling you, like I said before, understanding the basic chemical concepts that I'm going to teach you in this class is going to help you tremendously to understand the physiological processes that are going to occur in the body. All right, I'm telling you this. I promise you, I'm going to try to make it as simple as possible. Please ask me questions. If I'm going too fast, I have a tendency to talk too fast. All right? Ask me a question that slows me down. All right? And that goes for you guys at home. All right? You guys can do the same. I'll do my best to notice if you guys are asking me a question. Okay. So this picture here is showing you the most common elements of the human body. All right? If you look on the left side there, you'll see the major elements. Okay, the ones that are in abundance in our body. And if you look at the top here, 65% of your body weight is made up of oxygen. That's a lot, all right? But oxygen's a gas, okay? But here's the thing. Remember, oxygen, when it combines with hydrogen, can form water, right? H2O, okay? So a significant amount of your body weight, that the oxygen is generated from the water that's actually in your body, okay? So when you look here at this picture here, okay, you see these chemical symbols, all right, O, C, H, N, C, A, and P represent, all right, the molecule, the element, okay? Oxygen, carbon, hydrogen. But if we come over here to the minor elements, all right, not all of the symbols match the first letter, okay? Like potassium is K, so that's something you're gonna have to memorize, okay? So you need to know that. All right, sodium is Na. That comes from the old Greek system that they used when they generated the periodic table, okay? So just keep in mind, all the other ones should be relatively easy. Well, iron too is Fe, okay? So the three that aren't like the others, potassium, sodium, and iron, just kind of commit that to memory, okay? All right. So let's talk about the basic components of an atom, okay? So I want you to think of an atom. We're going to use what's called the shell model, all right? A model that's going to help depict what an atom looks like, all right? And think of the universe, our known universe. The sun is at the center of our universe, okay? So that's going to be what we call the nucleus of an atom, okay? So it's going to be in the center here, all right? And then you've got planets that orbit the sun, okay? Well, in the nucleus of an atom, you've got subatomic particles that will also orbit the nucleus, okay? And we're going to talk about those, okay? Okay, so let's start off with the first one that's listed here. There's 3 subatomic particles. The first one is called a neutron. Look at the first 3 letters of neutron, N-E-U. Neutrons are neutral. That means they do not have a charge, okay? They're not positive, they're not negative. They are neutral, okay? They have a mass. They actually have mass. We've assigned them a 1 on the atomic mass scale. It's not terribly important to know that, okay? Well, they live here in the center of the nucleus, okay? So they don't go anywhere. They're in the center, like the sun is in the center of our universe. The neutrons are in the center of the atom, in the nucleus. They live there, they go nowhere. All right, the next subatomic particle is the protons, okay? They also have a mass of 1 AMU, okay? But these do have a charge, P proton, P positive, okay? So they have a positive charge of +1. All right, so if I have 2 protons, then I have a positive charge of how much? +2, and so forth and so on, right? 3 protons, 4 protons, +4, okay? So keep that in mind, right? So both the protons and the neutrons live in the nucleus. They are not going anywhere. They're stuck there. They're not leaving, okay? The third subatomic particle is this guy right here, the electrons. Now, if you look here, their mass is 1/18th, wait, 1/1800, all right, of a proton or neutron. Point being is, I don't need you to know that, all right, but they're really small. They're just tiny. They're tiny and they barely weigh anything. So when we're talking about the mass of an atom, they don't really contribute too much to the mass, okay? So they're virtually nothing, okay? But what is important to know is that they have a negative charge, all right, and they carry a negative charge of -1, okay? So they live here in these shells or orbitals. So they orbit around the nucleus like our planets orbit around the sun, okay? So normally what we'll see is for every proton, you'll have an electron, okay? That's normally what we'll see, okay? Because remember, protons have a positive charge of +1. Electrons have a negative charge of -1, okay? So a +1 will cancel out a -1, okay? If you have more negative charges than you do positive charges, then we have an ion, okay? Well, I'll get into that. And vice versa. If we have more positive charges than we do negative charges, we also have an ion. Remember, because an ion is a charged atom, all right? It's a charged atom that it's either positive or negative, okay? We'll get into that. But keep in mind, we have these orbitals here, okay, around the nucleus. Now, the first orbital here, all right, the one that's closest to, this is worth noting, it's worth noting, okay? The first orbital can only hold 2 electrons. You write that down because that's been a test question before. 2 electrons. That's the most it can hold. Okay, the outermost orbital, there's a name for that, but the outermost, all right, the last one that you see, all right, it can hold a maximum number of 8 electrons. Okay, the outermost. There's a special name for that orbital. We call it the valence shell or valence orbital. That's its name. You want to make sure that you know that. Okay, so the innermost one, the very first ring, can only hold 2 at the most. The outermost, all right, holds 8. The valence shell. Okay. All right. All right, so I mentioned that we're just going to do a quick review here. All right, I talked about what the chemical symbol is. That's that letter there, okay? And it's unique or special to that element. So like I said, iron has Fe, sodium has Na, carbon has C, oxygen has O, all right? Hydrogen has H, okay? Nitrogen has N. All right, so it's a specific letter, all right, that we use to identify, all right, that element, okay? And in some cases, it includes more than one letter, like calcium, C-A-L-C-I-U-M, is how we spell calcium. Its chemical symbol is Ca, okay? So again, some of this you'll memorize, and trust me, as we move through this course, you'll know it, all right? We'll repeat this stuff so many times. All right, so when we're looking here at the periodic table, all right, each element has what we call the atomic number, okay? And that is the number of protons. So keep that in mind. So if someone asks you what the atomic number of an element is, all right, that's the number of protons that it has, the number of positive charges that it has, okay? So when we want to figure out how much an element weighs, all right, the atomic mass, we're going to add the protons and the neutrons together. Remember, the electrons are so small, they're so tiny, we don't even really count them, okay? Plus, they're flighty. They come and go. There's no purpose. So we'll just add the protons and the neutrons to get, sorry. I don't think I spelled that right. There we go. All right. So when we talk about a couple, okay, going on what I just said, all right, to determine the atomic number, we look at the number of protons. Okay. Now, knowing what we know, all right, you're welcome, Zach. Knowing what we know, all right, when you want to figure out what the number of neutrons that are present, okay, you can use this equation here. All right, so you take the atomic mass, which is both the protons and the neutrons, then you subtract the atomic number, which is the number of protons, all right, and that will give you how many neutrons that you have. So this example here says for sodium, okay, the atomic mass of sodium is 23. Okay, its atomic number is 11. Okay, so obviously you can do the math. This is how many neutrons we have is 12. Now, like I said, the electrons will always try to match the protons. Remember, opposite charges attract. Okay, positive will attract a negative and vice versa. Okay, so if you have 11 protons, normally you have 11 electrons. Okay, and that'll be a neutral element. Yes, ma'am.
Is the protons how they label them on the periodic table with
Yep.
that number at the top?
Yep. Okay. So let me show you a picture here when we're talking about diagramming. This is that shell model I was showing you. Okay. All right. So we're dealing with this element here that has, all right, an atomic number of 8. Okay. So that means it has 8 protons in the center. Okay. And it also has 8 neutrons in the center. So like I said, when we have 8 protons, we should have the same number of electrons. So you can see there's 2 electrons in the first shell. And then in the outer shell, in our valence shell, you can see that we have 6. Okay. So each of these shells, all right, or orbits, okay, that surround the nucleus have a specific energy level. Okay. That's as much as I'm going to go into, because we can get into a whole lot of chemical properties there. All right, but I want you to understand that, all right, that this energy level can change depending on how big or small the element is. All right, the more shells that you have, all right, it'll change the energy level, all right, of that element there. Okay, so keep in mind, and again, for our purposes for this class, the only numbers that I need you to know in regards to how many electrons can fit into what shells is 2 in the innermost, and in the valence shell, the outermost, up to 8. Okay, that's all you need to know. Okay, so when an element gains, all right, is going to add on these shells or these orbitals, it has to fill up the innermost orbital first. When that fills up, then the next orbital will start to fill up. When that one fills up completely, then the next one will start to fill up. Okay, so we start from the inside and we fill them up on the way out. Okay, all right. So let's get into chemical stability. All that stuff I just wanted to get out of the way here. Questions so far? A lot of that's just memorization. This stuff here, well, it's still memorization, but still. Okay. When we look at the periodic table, okay, your periodic table is made up of, all right, it's going to be made up of columns, which go from the top down, and then rows, which go from side to side. Okay. So when I'm talking about this, I want you to understand that's what I'm referencing. All right. So when we're talking about the periodic table, all right, the columns, all right, are going to represent how many electrons are in the outermost shell, which is the valence shell. Okay. So it starts with the lowest number here on the left, and then as you move to the right, the number gets larger. Okay. So over here, column 1A, these elements have 1 electron in their valence shell. Hydrogen, lithium, sodium, potassium. The only ones that are really important, don't worry about lithium for this class. So hydrogen has 1 electron in its valence shell. Sodium has 1 electron in its valence shell. Potassium, same thing. Okay? So 1 electron in the outer shell. It's important to know because we're going to talk about that concept here in a moment. Okay? So as we move to the next column, all right, that would be column 2, all right, 2A. That means how many electrons are in the valence shell of that column? 2. Okay, yeah, that's all I need you to know. So when we get to this column here, column 7A, all right, and this one here, all right, this one wants to have a full valence shell. Now this is the part that, trust me, is confusing to folks, all right? So first of all, there's a misprint on that. That should be 8, okay, in order to have a full valence shell, okay? So understand something in nature, and we talk about this with homeostasis. Your body always wants to be in balance. It wants to be healthy. Well, everything in nature wants to achieve what we call homeostasis, but when we talk about chemistry, they use a different term. They call it stability, okay? When we fill that valence shell, when there's 8 electrons in that valence shell, all right, then that atom has achieved stability. It doesn't want to do anything, okay? It's done. It's full, all right? Just like you when you've eaten a big meal and you don't want to do anything after you've eaten the big meal after Thanksgiving, what do you want to do? You want to sit down and maybe rest on the couch? You don't feel like running a marathon. Maybe you do. But you're going to when the valence shell gets full, that element, all right, that atom won't want to react with anything, okay, all right, because it's stable, it's filled its valence shell, all right, and we refer to, all right, that column as the noble gases, okay, and the chemical term that we use is inert, which means they don't want to react with anything. They're stable, they're cool, okay. Again, that's not really terribly important for biochem, but this is where we want to start to move into to kind of give you an understanding here, okay? So remember what I said. There's attractive forces. Things are molecules get held together by 2 things, by attractive forces and chemical bonds. All right, so we're going to start to move into that. So the first type of compound that I want to talk to you about, of chemical compounds, are ions and the ionic compounds, okay? So these chemical compounds, all right, are what we're going to see when 2 or more elements all right, kind of come together, all right, to form what we call a molecule. Because you guys remember what a molecule is, two or more, all right, atoms that come together, okay? So we're going to start to form these molecules, all right? So the actual coming together of these molecules, all right, we're going to refer to as chemical compounds. And there's two types, an ionic and a molecular, okay? So we talked about ionic compounds. Excuse me. We talked about what an ion is. What's an ion?
Positively charged atom.
Yeah. It's a positive or negatively charged atom, okay? So what happens, what do you think happens between one positive ion and one negatively charged ion? What do you think they're going to do to each other?
Attract.
Yeah, opposites attract, right? They're going to probably come together. Two positive ions, what do you think they'll do to each other? They'll repel. You ever work with magnets? Two north poles push away from each other. Two south poles push away from each other. Like charges, and as do like poles, they push away from each other. So that's what we're going to see here. So these ionic compounds that we're going to see, we're going to witness what happens when two ions, all right, that are attracted to one another. They're going to form this crystal lattice structure. We'll talk about that in a second. But how they do that is through ionic bonds. So we're going to talk about what an ionic bond is here. Okay? All right. Just to recap, an ion, all right, is going to be an atom with a positive or negative charge. Make sure that you put a star next to that and you know that. Okay? So remember what we said about atoms. Okay? If you have an atom with 8 protons, all right, it's going to want to have 8 electrons. Okay? So therefore, it won't have a charge. So what happens, all right, when one electron, all right, leaves that atom, or what happens when one electron comes to that atom, all right? You're going to have more or less electrons than protons, okay? So that's essentially what an ion is. So either we're going to lose an electron or we're going to gain an electron or more. It doesn't have to be 1, it could be 2, okay? So an ion is created when we lose or gain 1 or more electrons. Okay? That's how we get these ions, these charged particles. And they have plenty of significant physiological functions. All right? Potassium, sodium, both are important in the functioning of our nervous system. Okay? Calcium is another one that's important in actual muscle contraction. All right? Clotting in our body. Calcium is also important in the actual functioning of your nerves. Everyone thought that calcium is needed for strong teeth and bones. Yes, but it's much more than that, okay? So we'll see some of these functions for some of these ions. All right, so let's start off with a definition of what a cation is. All right, a cation is when we lose electrons, okay? So I always think of a cation because I do like cats, and cats are soft and fuzzy and cuddly. So when I think about a cat, it's a positive emotion. I don't hate cats. So that's how I remember what a cation is. So when we lose, all right, normally, what did I say? 8, I'll keep using the same example. 8 protons, 8 electrons, okay? When we lose 1 electron, now we have 7 electrons, all right? We have 8 positive charges and 7 negative charges. What's the overall charge of this element going to be? It's 1, but what is it? Positive or negative? Positive. That's right. Good, good. So that's a positive. All right. Ion. So therefore, it's a cation. Cool? Good so far? Okay. All right. So we're going to see that with sodium. All right. Na. Normally, when you'll see me write it down, hopefully I'll write it correctly, is usually Na plus. Now the plus means that there's no number associated with the plus. It's always understood to be 1. Okay? So if it's calcium Ca2 plus, then that means we've lost 2 electrons. If there's only a 1 plus sign, that means we've lost 1 electron. Or if the element has X3 plus, then we've lost 3 electrons. Okay? So if you don't see a number associated with this, it's always just 1. Okay? All right. So I'll explain this. I haven't talked about the octet rule, have I? Okay, I'll talk about, well, let's talk about the octet rule. So this is what happens to sodium. I'm going to come right back to this picture here. There we go. Let me zoom in here. Don't pay attention to the rest of the stuff here. I just want to show you what sodium looks like. Oh, sorry. All right, so here's sodium, okay, with all its shells. Okay, so the innermost shell has 2, and then as we move out, okay, the next shell, it has 8, and then its valence shell has 1, okay? So let me ask you this. Now remember, stability for an ion, for an atom, it always wants to have how many electrons in its valence shell? 8. We call that the octet rule, all right? Every single element wants to have 8 electrons in its valence shell. Okay, so let me ask you this. Would it be easier for sodium, okay, to gain 7 more electrons or give up the 1 electron and have this outer shell disappear and then have this shell be the new valence shell? Right, much easier to do that, okay? So when it gives up this electron here, it now has lost that shell, but now look at its new valence shell. It has 8 in the valence shell. It still has 11 protons, okay, because those don't go anywhere. But it has 2, 4, 6, 8, 10 electrons. It has more protons than electrons. It gets a +1 charge, okay? So the octet rule states that an element always wants to achieve stability, all right? Its tendency to always try to fill its valence shell. And it'll do that by either donating electrons, so it loses its outer shell, or it will try to gain electrons to fill its outer shell. But its goal is to always fill that outer shell. And that's the octet rule, okay? Let me go back to this here. So this is what we're talking about here. So sodium can reach its stability by donating that 1 electron. So now it has a new valence shell, okay? And it's happy. And it satisfies that octet rule. So make sure that you write this down if you haven't done it already, okay? It's the element's tendency to lose, gain. We'll get into the sharing of electrons, all right? That's a different type of bond, all right? Sharing of electrons to complete the outer shell, okay? All right, so it went from having 11 protons and 11 electrons, now it went to having just 10 electrons. So its overall charge is +1. Okay, so make sure that you know a cation has a positive charge. Are we good so far? Am I moving too slow? I can go faster. Okay, all right. Okay, so let's talk about the opposite. Okay, so what happens, all right, when we gain electrons? So we're going to start getting more negative charges. So we have a special name for those ions, and we call those anions. Okay, so they will have negative charges. So we're going to use chlorine as our example. So I'm going to come back to the slide here. So every orbital can hold 8 electrons except the first one. Yes. Okay. So let's go back to that picture, bless you. All right. All right, so here we can see chlorine. There we go. Okay. So again, you can see in its valence shell here, it has 7 electrons. So again, would it be easier for this element to gain an electron or give up 7? Yeah, just gain one. Yeah, easy. Okay, remember, in nature, things want to do things. Certain processes want to occur to achieve stability, but also nature is lazy. Doesn't want to expend a lot of energy to do so. All right, so it's much easier to gain 1 electron than to lose 7. Okay, so that's what's going to happen here. All right, it's going to get an electron from somewhere, and when that happens, all right, now it's filled its valence shell. But when we count up the electrons, okay, and compare it to the protons, all right, we have 17 protons, but we have 18 electrons. That's how we get a negative charge there. Okay, remember the difference between the protons and the electrons. All right, will tell us what the charge is going to be. All right, if it's a difference of 2, but there's more electrons, it'll have a -2 charge. Okay? All right. Where are you? There we go. Oh, that's cations. Boom. All right, here we go. So again, all right, chlorine is going to try to reach its stability by gaining that 1 electron, what we just saw. We've established our octet rule, okay? But our situation now, we had 17 protons. That doesn't change, but now we have 18 electrons. We've gained 1 electron, therefore the overall charge to that molecule is -1, okay? So anions will always have a negative charge. Cations will always have a positive charge. So we have a term here called polyatomic ions. All right, they're anions. All right, but they're going to have, all right, more than one. Okay, more than one atom in that molecule. And so the example, there's 2 examples, but I'm going to just tell you about bicarbonate. Bicarbonate is a chemical buffer. I'm not going to go into the details. All right, HCO3. This is the molecular formula. Okay, but that's a polyatomic ion. All right, there's a couple anions here. All right. So all that to explain to you what an ionic bond is. Okay. Real simple. Make sure you know this definition. All right. So an ionic bond is simple. It's 2 oppositely charged ions that are attracted to one another. Okay. Or to use the definition that's up here, you're going to have cations and anions that are bound to one another through what we call electrostatic forces. Simple enough. What's an electrostatic force? Opposites attract. Positive and negative charges, opposite charges will be attracted to one another. All right, so we refer to that as electrostatic forces. You'll have to forgive me. I'm going to tell you this right now. Probably, when does allergy season start around here? Like October? You know how we have like, this late September. Anyways, I'm going to lose my voice then. I'm just predicting that. It happens twice a year. Once in the fall, once in the spring, because I talk too much. Okay, so this is how salts are formed. You guys have heard of table salt, right? Sodium chloride, that's what this is. Sodium, Na, sodium, Cl is chloride. So that slide that I was showing you, those pictures over there, all right, that's table salt. And I'll go back to that slide here in a second. So we saw that sodium, its valence shell has 1 electron. So it's going to donate, all right, its 1 electron to chlorine, all right, because it has 7 in its valence shell. All right, so when it gives up its 1 electron, sodium becomes positively charged, chlorine becomes negatively charged. So what did we say? Electrostatic forces, opposites attract. Those 2 ions will be attracted to one another. Okay? So let's see a picture. This is what we saw. All right, so here we see sodium. It's giving up, donating its electron. Okay? And now it's positively charged, and chlorine, or chloride now, is negatively charged. So they're going to bind together and form this structure here, which is what we call the lattice crystal structure. Okay? And this gives us table salt. All right? So this configuration is determined through those electrostatic forces of positive and negatively charged ions being attracted to one another. That's what we're seeing here. Okay. Questions so far? Not too bad, right? Not too bad. I'm telling you, if you're confused, it's okay. Just know that these will be posted on Blackboard, and you can sit at home this weekend, all right, watching them again. Okay? Yes, ma'am.
We're going to have to do any of that on the test, like balance and back out.
No, you won't have to know that, but you'll have to know like the definitions and certain concepts. It won't be anything too bad, but you'll have to know like the octet rule, all right, electrostatic forces, opposites attracting, that sort of thing. All right, so we talked about what happens when one molecule donates an electron to another molecule and vice versa, okay? All right, that's one type of bond that can occur. Another type of bond that can occur is what we call a covalent bond. okay? And as soon as you see the term covalent, I want you to think of kindergarten. I learned a very important lesson in kindergarten. I learned how to share things, and that's what a covalent bond is. It's a bond that the elements or the atoms are going to share electrons with one another. Okay, sharing is caring, and that's what we see these atoms doing. They're caring for one another by sharing the electrons that the other atom needs, and it satisfies them both. All right, instead of giving up the electron completely, now you're going to see some of these molecules, or excuse me, these elements or atoms share with one another. Okay? So here's the thing. When we talk about a covalently bonded molecule, all right, they're going to be sharing electrons between each other, but it's going to be two or more atoms, but they're going to be different. Okay? So when that occurs, we give them a new name, a molecular compound. So here's an example. Carbon dioxide, carbon and oxygen. All right, those are different elements, okay? But molecular oxygen, all right, is the same, okay? So it will not be a molecular compound, okay? They have to be different elements. So I'll get into the configuration in a second here, okay? But what I really want you to know is a covalent bond is the sharing of electrons between two or more different atoms. Wow, it's hard to drink through a face mask. I just put this up. I can't drink this way unless you can tell me. I'm just straw. Okay. Questions so far? Okay. So let's move on to the next one here. Normally, in my normal slideshows, when I do this in PowerPoint formation, these are questions, all right? But this is a PDF to save space because it's a smaller file. I have to download these as PDFs. So the question and the answer will appear at the same time. I'm not crazy about that, but that's just the way it is. All right. So could an ionic bond form between two cations? And you guys probably already saw the answer. I wasn't able to switch it off fast enough. And I'm going to actually do the next one here. Oh, you'll still be able to see it, so forget it. All right. Anyways, so let me read the question. Could an ionic bond form between two cations? And the answer is no. And the reason why is why? Tell me why. Yeah, both positive. They're like charges, and they'll repel each other. They'll move away. Same thing with two anions. Two anions will not form an ionic bond because they'll push away from each other. The only way you can form an ionic bond is if you have opposite charges. That's simple. Okay? Keep that in mind. Okay? So that's what we're seeing here. Okay? Positively charged cations and negatively charged anions may form ionic bonds with one another. A cation and another cation cannot form the electrostatic interaction needed. In the same way is true with anions. Okay? They both want to do the same thing, and they can't. One has to give, the other one has to take. That's how it is. Okay? They're only true in life. Okay. So we talked about the two types of bonds: ionic bonds, covalent bonds. Now we're going to talk about how we write all these relationships out. So you need to know how to write out a chemical formula. All right, because we're going to use terms like what I wrote earlier, what bicarbonate was. All right, HCO3. All right, that's a molecular formula. Okay, and so what a molecular formula is a recipe. Okay, it's literally a recipe. All right, for those of you that like to cook and bake, I hate doing either or. I don't have the patience for it, plus I'm horrible at it. All right, after I took microbiology, I overcook all my food. Okay, I'm terrified of foodborne illnesses. So, except I will eat a steak medium rare. Okay, I can't do a well done steak. All right, I can't cook out all the nutrients. It just doesn't sit right with me. Anyways, so a molecular formula is basically a recipe. It tells you what's in it, whatever we're looking at, and how much. Okay, so that's what we're seeing here. It's going to indicate, all right, the type of atom. Okay, so what's in whatever we're making, and then how much, the number of atoms in our molecule. Okay, so this example here, carbonic acid, H2CO3. All right, so what the small number means, it indicates how many atoms are present. So H2 tells me what? How many hydrogen atoms? 2. All right. Carbon, how many carbons? 1. is only because, look, if there's not a number preceding it directly, then it's understood to be 1. Okay? So, and then for oxygen, 3. Right, okay, good. So keep that in mind. So like with H2O, same thing. How many hydrogen?
2.
How many oxygen?
1.
Booyah. Okay, simple. Simple, simple. So when we're looking at bicarbonate, how many hydrogen? How many carbon? How many oxygen? There you go. Okay, good. You guys are chemists now. Perfect. All right. All right, so we got the molecular formula. The molecular formula tells us what's there and how much. So now we want to see what it looks like, though. All right, I want to see a 3-dimensional diagram. So that's where the structural formula comes into play. All right, it does the same thing that a molecular formula does. It's going to tell us what type of atoms are involved and how much, but also it's going to show us the arrangement, how they appear. Okay, so what it looks like. Okay, so the structural formula includes one more thing. All right. So we're going to see here, all right, with carbon dioxide. This is not. I'm going to show you a better picture, so I'm going to skip that example. All right, but before I go on, I should probably tell you what an isomer is, because you can have certain molecules that have the same exact molecular formula, all right, but structurally they're different. Okay, our simple sugars are like that, or our monosaccharides, glucose, all right, galactose and fructose. Those are all monosaccharides. They have the exact same molecular formula, all right, but their structural formula is different. I'll show you what I mean by that is. All right, so that's what this is. All right, so isomers are essentially the same type of elements, right? They have the same number of ingredients, but they just look different. They're arranged differently. So I'll show you what I mean by that is, so you don't think I'm losing my mind. Okay, so let's look at glucose, okay, and galactose and fructose. Here's the molecular formula, C6H12O6, and it's the same for all of them. So they have the same number of carbons, same number of hydrogens, and the same number of oxygens. All 3, all right, of these compounds. Except if we come down here to the picture, right, when we're looking at the picture, the structural formula, all right, you can see that this molecule, the glucose, it has a hexose ring. Okay, it has 6 carbons. This one has another hexose ring, but this is a pentose ring. This means it only has 5 carbons in this ring. This one has 6, and this one has 6. So we stick its carbon somewhere else. Point being is, they'll have the same number of atoms. They're just arranged differently in space, so they'll have some different properties. Okay, so those are called isomers. All right, so keep that in mind. So make sure that you understand they'll have the same ingredients. The molecular formula will be the same, but the structural formula will be different. All right. So what information about a molecule is gained by a structural formula? What does the structural formula tell you? I didn't put the answer up there. Can you read that on the screen? It tells you the arrangement. Okay, that's what the structural formula does. It shows you the arrangement and it tells you how all the molecules are arranged. Okay, so what about, how does this differ from a molecular formula? What's a molecular formula tell you? Right. Does it tell you the arrangement? That's right. Good. Yep. Okay. So that's what we're seeing here. Okay, structural formula shows you the arrangement. All right, molecular formula, well, a structural formula tells you the type and the number and the arrangement. All right, molecular formula tells you the type and the number, but not the arrangement. All right, good. All right, so let's talk about more in detail these covalent bonds. All right, so true or false, covalent bonds donate or gain electrons? Pardon? They share them. So the answer would be false. That's right. Yes. So covalent bonds are sharing of electrons. All right. Ionic bonds are donating or gaining electrons. Okay. That's what we get with the ionic bond. Good. 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 All right. So keep that in mind. Underline this term. Atoms share electrons. Okay. So this is what happens when both elements or both atoms need electrons. They got to get it from somebody else. Okay. So they're going to go to another element that also needs electrons, And so they're going to share amongst themselves. And that's what we're going to see here. Normally, we'll see that with elements that need between 4 to 7. Okay? Well, I shouldn't say they need 4 to 7. They'll need roughly 1, 2, 3, or 4 electrons possibly. So what does that mean? If you have 4, 5, 6, or 7 electrons in your valence shell, you're most likely going to form a covalent bond. Okay? It's not 100%, but if you have 4 to 7 electrons in your valence shell, you're most likely going to create a covalent bond. And I'll show you a picture here in a second. So in our bodies, these 4 elements here, okay, hydrogen, oxygen, nitrogen, carbon, those 4 elements are going to form covalent bonds. Okay? If you look at the first 2, all right, they make up close to 70% of your body mass. Hydrogen and oxygen. Carbon, from a chemical standpoint, if you have carbon in the molecular formula of anything, it's considered an organic compound. Okay? You have to have carbon in it. That's the definition. I got into an argument with a teacher about that. They had to Google it, and I knew I was right. Okay? But if you have carbon anywhere in the molecular formula, it's an organic compound. All right? So let's talk about covalent bonds. Okay? So we're going to figure out how to make covalent bonds. All right? And we'll start with the simplest covalent bond that we can form. And we're going to use 2 of the smallest elements, hydrogen atoms. Okay? So a hydrogen atom, I'm going to come back to the slide. A hydrogen atom, here's a hydrogen atom. Okay? Here's the nucleus. Here's its 1 shell, and it's got 1 electron. Okay? So its atomic number is 1. All right? But again, how many electrons can it fit in the shell? 2. 2 is the maximum. Remember, the first shell can only hold 2 electrons. Right? And in this case, this is hydrogen's valence shell. Okay? All right. So it's going to want to share an electron with another molecule. Okay? So if there's another hydrogen atom floating around and it also has 1 electron, it's going to share those electrons. So this hydrogen atom is going to share these 2 electrons, and this hydrogen atom is going to share these 2 electrons. And they're going to hang out with one another. Okay? So they both satisfy their octet rule. In this case, since it's the first shell, it only holds 2. All right, but we still use the octet rule name to understand that. When we get down here to water, okay, oxygen has 6 electrons in its valence shell. So that's why oxygen can create 2 covalent bonds. Okay, you can see it's sharing, all right, these 2 electrons, and whoops, these 2 electrons. Oh, I'm not going to circle that. Carbon, it's got 4 in its valence shell, right? You can see the blue represent the carbon electrons, and then it can form 4 covalent bonds with 4 individual hydrogen atoms. Okay, it varies depending on what's available. So let's go back to this slide here. Okay. So that's what we're talking about. Hydrogen will share with another hydrogen or oxygen or whatever. Okay. It's not picky. It just needs to fill its valence shell. Okay. So one of the simplest forms of covalent bonds is what you see between 2 hydrogen ions or atoms. Okay. Same thing with oxygen. Nitrogen can form 3 bonds. Okay. So that means it's got 5 electrons in its valence shell. So it wants to get 3 more electrons. So ammonia, all right, NH3. Okay, so you have your nitrogen. Whoops, that's not nitrogen. That's oxygen. Can a molecule not have any electrons? Is the hydrogen giving up its electrons? Yes, a molecule can. So hydrogen can give up its electron. Okay, and off the top of my head, I cannot tell you the name of that. That's an organic chemistry question, but it can. But again, I can't remember what the name of that is. I apologize, Heather, but it can. So nitrogen will then form 3 covalent bonds with hydrogen. And it looks like this kind of configuration. Whoops. Okay, so the nitrogen will be up here at the top, and then you'll have 3 hydrogen ions floating down below it. And then you saw what carbon looks like, all right, when it has its 4 hydrogen bonds, right, it's all surrounded. And that's what actually methane is. Cow farts. Seriously. All right, so covalent bonds, all right, you can have single, double, and triple covalent bonds. So obviously, when you want to know this relationship, when you have 1 single covalent bonds, that means that you have 1 pair of electrons being shared, all right, between 2 atoms. All right, if you have a double covalent bond, that means you have 2 pairs being shared. And then a triple covalent bond obviously means 3 pairs. Okay? I'm going to show you a picture here and come right back. All right, so if we zoom in, here you can see, all right, here's the single covalent bond between 2 hydrogen atoms. And then you can see here's a double covalent bond between 2 oxygen atoms. And then we got our triple bond between 2 nitrogen. As you can see, they're sharing all of these. All of these electrons are being shared. So if you're going to write this out on a piece of paper, these are the symbols that you would use. So to represent a triple covalent bond, it would be N with 3 dashes in between. All right, for a double, it would be 2 dashes in between the 2. And then obviously a single is 1 dash. Okay? I'll go back to the previous slide. All right, any questions on that? No, okay. Fair enough. All right. So keep in mind, all right, what we talked about. Octet rule. We need to find different ways. And this is just showing us, all right, all the different ways that certain atoms, in this situation we're talking about carbon, you can see all the different ways that carbon is actually going to try to satisfy its octet rule. It can get, all right, 4 hydrogen. It can look for 2 oxygen, all right, and form, there's our carbon dioxide, okay, or here's gasoline, ethanol, right? So it takes a combination, all right? Carbon can bond with another carbon, it'll fill up with some hydrogen and even some oxygen, okay? It's just whatever's available there. All right, so there's a variety of different ways that carbon will actually try to satisfy the octet rule there. Don't worry about that. All right, let's talk about nonpolar and polar covalent bonds. Okay. So planet Earth has a North Pole and a South Pole, okay? So when we're talking about, and what those poles are, they're just parts of the Earth, all right? So, one end, I guess you could say, or one portion of the Earth, the other one's on the opposite part of the Earth. Well, when we talk about polar and non-polar covalent bonds, we're going to now give parts of a molecule that are not ions, but certain parts of a molecule will have more of a negative charge to it, and certain parts of the molecule will have more positive charges to it. Now, I'll explain what I mean by that. That's what this non-polar and polar covalent bonds come in. So first of all, you want to understand the term electronegativity. Make sure that you have this written down, okay? So when we talk about the electrostatic forces, that's the attractive forces between opposite charges. So what we're seeing with electronegativity, all right, this is the relative attraction of each atom for electrons. So some atoms will have more of an attraction to electrons than others. Okay? So hydrogen might have more attraction to electrons than, say, iron does. Okay? Or oxygen might have more than carbon. Or my point being is that some specific elements will have more of an attraction for electrons. They're greedy. Think of them as being greedy. All right? They're greedier. Some are greedier than others. Okay? And so this is how we'll determine, okay, how these covalent bonds, how these electrons are shared between those elements. Okay? So here's the thing. When we're talking about covalent bonds, all right, between two of the same element, all right, if it's the same exact element, they're going to have equal attractive forces, right? Does that make sense to you guys? All right, so if they're the same element, they're going to have equal attraction for those electrons. Okay, two oxygen are going to form the same amount of attractive forces on those shared electrons. All right, so they're going to be what we call nonpolar. Okay, nonpolar. One part of that molecule is not going to have a more negative portion, and one part's not going to have more of a positive portion. It's all shared equally. Okay, so that's what we call a nonpolar covalent bond. Okay, when we get unequal sharing of electrons, okay, when the electrons are drawn closer to one element more than the other, okay, then we refer to that as a polar covalent bond. You guys get that? You guys get that at home? Okay. You do? Okay. All right. Because this is what's going to kind of explain some things while, even though there's no ionic elements involved, how can certain elements have a negative charge on one end of it, like amino acids. Amino acids, which we'll talk about, one end of an amino acid is negatively charged and the other end is positively charged. And it has to do with these covalent bonds that occur, okay? All right. So when we're talking about, I'm not going to worry about that portion there about which part of the periodic table. Well, I'll go over it with you just in case it's asked on the test, okay? So when we're talking about the periodic table, remember, this is my horrible drawing of the periodic table. Remember, we have our columns, top to bottom, okay, and then our rows, side to side. All right? So when we're looking at the periodic table, when we go, like reading a book, from the left side to the right side, okay, as we are looking from the left to the right of the periodic table, the electronegativity increases. That means the elements on this side of the periodic table are greedier. Okay? They're going to pull electrons. If they're making a covalent bond with another element, they're going to pull those electrons closer. Okay? They're going to have the majority of the electrons. Okay? So they're greedier. Okay? Also, if we go from the bottom of the table up towards the top part of the table, those elements are greedier also. Okay? So the elements over here in the right top corner are the greediest of all elements. All right? They're going to draw electrons closest to them. Okay? All right, just so keep in mind. So that's what we see here at this bottom portion here, that hydrogen, okay, is going to be the least greediest, all right, out of those four elements that we see in the body, all right. Oxygen is going to be the most greediest, okay. Most, you say that, most greediest? Or, yeah, right. It's going to be the greediest. Right? It's going to want to take all the electrons and hold it close and not share with hydrogen. Okay, so keep that in mind because I'm going to show you a picture here in a second. All right. So when we see, like when you saw me earlier drawing out oxygen, oxygen looks like this. Its structural formula is going to look something like this. Okay. So what will happen is, remember, there's two electrons, all right, that are in this covalent bond here and two here. So oxygen is going to draw these electrons closer to it. Okay? So when it does that, it's going to make this portion of the molecule more negative, and therefore, by default, this portion of this molecule, the water molecule, the part closest to the hydrogen, right, is going to be positive. Anyways, this phenomenon is what allows water to stick together as well as it sticks together, because there's attractive forces between water molecules, okay? So that is why water has the properties that it has, its boiling point. I won't get into that because you don't need to know that for this class, okay? But it's because of these electronegativity that water has its properties that it has, okay? Water, essentially, you ever notice how water will kind of, if you look at a glass, water kind of sticks on the sides of the glass, all right, because it's attracted to that area there, okay? Anyways, so what we're going to see is, since electrons have that negative charge, all right, if those negative charge electrons are gravitating towards one molecule more than the other, then it's going to give that molecule more of a partial negative charge, like in this drawing here, okay? And because of that phenomenon, okay, as we see the electrons being closer to oxygen, the hydrogen atoms are going to have a partial positive charge because they're less electronegative. So the greedier molecule is going to win out, and it's going to have, all right, more electrons around it more often, so it'll be more negative, okay? All right. Oh, yeah, actually, I'm going to stop here. I would love to get into water as a neutral solvent. Oh, let me just mention that last part here. Sorry, guys, at home. All right, so we have an exception to the rule. And in this class, there's going to be a couple exceptions to certain concepts that I'm going to be going over with you. So the exception to the rule is in this situation here when we have a polar bond between two different atoms. All right, so when we're talking about carbon and hydrogen. Okay, so we saw that in methane, going back to this picture here. All right, come back. Oh, there it is. All right, so here you can see in this situation here, all right, with these two different atoms here. Oops, going the wrong way. Okay. Any questions, you guys? I know it's a lot to take in. I figured this is a good place to stop. Anyone at home? Questions, questions? You guys are quiet. Was that a lot? You think so? Yeah, I know. Trust me. I know chemistry, it's like growing pains, guys. This part here, even though I find it to be interesting, the basic concepts are going to be important for you to understand, and that's why I'm saying understand what ions are and what creates those ionic properties in covalent bonds. All right, you want to know what electrons are. All right, what and that property or that I know it's a lot. Yeah, that property that when electrons leave an element or come to an element, that it can make that element either positively or negatively charged. Because that's going to create some of the properties and some of the behaviors that we're going to learn about. I promise you, it'll get a little bit less difficult, a little bit more interesting as we make our way through once we get to the cells, and then we'll get to tissues, and then we'll get to the actual systems. All right? I know that chemistry can be a little bit boring, but it's really important that you understand some of these concepts, okay? So, so you'll understand some of the physiological processes that occur. Are these slides on the blackboard? I would like to print them before the lectures and make notes on them. Okay. Tara, I cannot put these slides up on the blackboard because of these are copywritten, and I'm not allowed to do that. And two, because the American Disability Act, not all students can have, if they have visual impairments, they can't utilize these slides. But these slides will be on these recordings there for you. So you're more than welcome to look at them there, all right? So they'll be made possible. I just cannot post them on Blackboard. The department does not allow me to do that. All right, let's take a 10-minute break. Okay, so for you guys at home, you're going to step out of this session and come into the lab session. All right, so I'm thinking let's do 10 minutes. All right, come back around 7:30. Hopefully we can get done. I say early. All right, I'm always going to try to get you guys and my other section at the same pace. So so we might be able to finish up early. So let's take a break. Please sign in. Okay, if you haven't signed in, and you guys at home, I'll see you in about 10 minutes. So meet back here at 7:30. Okay? I don't expect to hear anything from you. You guys are quiet at home. All right. I'm going to stop the recording. Take a break. Don't